All right, our next presentation is the Urban Drainage Design HEC-22 4th Edition Manual Update and Curb Opening Inlet Equations. We have two presenters for this session. Ryan Lizewski is a hydraulic engineer with FHWA's Resource Center, having 15 years of experience in the field of hydraulic engineering. Ryan was hired into the Resource Center last year with his prior experience in the private sector, providing consultant services in the Northeast. Ryan specializes in many areas of hydraulic engineering, including urban drainage, stormwater management, floodplains analysis, and hydraulic modeling. Ryan is currently the technical lead for the HEC-22 Urban Drainage Design Manual Update and several of FHWA's National Highway Institute courses. He graduated from Worcester Polytechnic Institute with a bachelor's degree in civil engineering. James Pagenkopf, did I say it right? Okay. Is a hydraulics research engineer in FHWA's Office of Infrastructure R&D, providing support for hydraulic and hydrological research activities conducted at TFHRC Hydraulics Research Laboratory. He was previously a research engineer providing over 12 years of contracting support at TFHRC for both the hydraulics and aerodynamics laboratories. Mr. Pagenkopf holds an ME and BS degrees in mechanical engineering from the University of Virginia. Please give him a warm welcome.
Awesome, thank you, Eric. So, my name is Ryan Lizewski, and I'm happy to be here to introduce the HEC-22 update, 4th edition. I don't have any really cool equations or fancy animations in my portion of the presentation, so please bear with me for a few moments, and then James will come up here to present some numbers and wake you guys up. So. Our terms of service here, and also just to mention, HEC-22 is still unpublished, the 4th edition. It's going through a review process. It's considered technically complete, but this review process takes some time, also limits exactly what I can present today. But hopefully it should be out on the streets pretty soon, and hopefully I'm not presenting the same slide deck at the next NHEC. The tech note that James will present on is published, and that's one of the ways that us at Federal Highway really try to disseminate information when we feel like it needs to get out there sooner rather than waiting for an HEC or an HDS update. So that was kind of our line of thinking on the publications of that document. So today I'm just going to give a quick overview of the HEC-22 Drainage Manual, which I know all you guys know nothing about, so this will be really engaging for you guys. But I'm really going to talk about the effective and resilient planning for storm drain infrastructure and how it fits into the design process. One of the updates that will be included with HEC-22 is some additional discussion on water quality treatment. So I'll briefly hit on that, and then like I said, James is going to come up here with the actual research and some cool numbers. So the HEC-22 Drainage Manual, it's a manual that provides comprehensive and practical design of stormwater drainage systems, and it's really meant and intended for use within the highway right-of-way to collect, convey, and discharge stormwater runoff. So this manual, as you guys are probably all well aware, provides the methods and procedures for the various hydrologic and hydraulic computations required to design such infrastructure. Honestly, with this update, a lot of the latest and greatest and everyone's favorite equations, many of them didn't change, but with this update, what we really strive to do is really bring it up to the level of the current industry practice, where we're using computer software to really make a lot of these decisions and calculations, and we try to streamline the design process and make it a more relevant document for today's engineers and designers. So, we have the methods and procedures for everything listed on the screen and more. Additionally, we have designs for detention basins, infiltration, stormwater quality units, and pump stations. So, and one thing we want to do with this HEC-22 manual too, as a goal of this manual is to support the planning, implementation, and stewardship of sustainable, resilient, and reliable transportation infrastructure. So when we talk about sustainability, we really talk about balancing the needs for the environment, social, and economic drivers of a particular project. So traditionally, we think of sustainability as balancing, the environment with the economic needs for the development and the transportation infrastructure. But we also want you to think about the equity component of that, where we're really trying to balance the social and economic components of that particular project. And once we consider all three of those in our design process and early on, we can really ensure that we're coming up with a sustainable and resilient design for our stormwater infrastructure. With sustainability in mind, what is the goal and how do we plan effectively for our urban drainage system? So really the ultimate goal is to design a highway storm drain system to provide safe and reliable passage of vehicles. So, we've heard today and we all know that, traffic safety directly relates to water on the roadway, and the quicker we can get that off the roadway improves the passage and the safety for the traveling public. And so how we do that is we really balance the needs between the design criteria, where we look at the function of the roadway versus the risk. The risk being damage and safety, damage to adjacent properties and infrastructure, damage to cars, traveling public, and the safety. And then resiliency. The ability to adapt, prepare for, and anticipate changes in conditions and withstand, respond to, and respond rapidly from disruptions. So, we included a lot of discussion on sustainability and resiliency in this document. Traditionally, when we do these type of designs, it's all stationarity based on past observations, and HEC-22 is not intended to be some sort of climate change document, but we want designers and engineers and owners really to start thinking about this early in the design process. We have other publications if we're looking at rainfall totals, stream flow increases, climate change, changes in land use, how that affects the hydrology. There are other documents for that. So, but we wanted designers to consider that when they approach storm drain structures and not just start kind of placing their inlets where they feel geometric controls are needed, but really take this holistic approach to drainage system planning. And really to have that effective and resilient designs, designers need to ask themselves a few questions. Have the impacts to quality and quantity been considered, and are they acceptable? What are the risks to the system, and have damages or service interruptions been considered and are acceptable? And then again, that changes in land use and climate changes and how that affects our design. We're designing for today, but how does that function in the future? And that ties into life cycle costs, cost to construct, cost to maintain, cost to repair. So all that factors into our design process. At the end of the day, we still need to place catch basins and inlets, and we still need to install pipe. So the new manual has this flow chart. We'll walk you through the design process. But really what we wanted to do with this update was really streamline it, make it a little bit more user-friendly, and really understand that people are using computer software to compute these. So we focus less on walking you through manual calculations and more on the meaning and how and why, and that way when you enter you use a computer program, it's not just a black box. You know what to look for. You know what the computer is doing. I don't know how many hundreds of structures and miles of pipe I've designed and put into the ground. I know exactly how many times I've manually iterated through these spreadsheets, which are in the existing version of HEC-23. So with that approach, we really wanted to understand whether you're using the hydraulic toolbox, SWIM, StormCAD, HydroFlow, HydroCAD, ICPR. There's countless programs out there that will do gutter spread, hydraulic grade line calcs. We really want the user and designer to really understand what's going on in the software and those computations so that they are able to effectively enter that data into the software, and then when it gets the results, have them be able to review that and understand the results they're getting are accurate, reliable, or if there is any issues, they know to start looking into it. And then stormwater quality. So water quality and water quality regulations are increasing a larger part of transportation infrastructure, particularly since the last issuance of this document. In the water quality section, we tried to lay out strategies and guidance for the selection of stormwater BMPs, which is heavily site dependent. And there's a lot of good research and even some FHWA publications and synthesis that provide good resources and a reference in order for the selection of a particular BMP practice for within your right-of-way. And then estimating pollutant loads, for both pre and post condition scenarios. So there's equations in there, but also reference the work of others. Recently, FHWA, in cooperation with the USGS, developed the highway runoff database and the Selden model. So if you heard Greg's presentation this morning, you went into more detail about that, but that's one of the new guidance that we've included within the document, and it really provides the tools and techniques to help transform that data into something meaningful when we talk about stormwater design and water quality within the highway right-of-way. And of course, structural BMPs, we still give you guidance on how to dig a hole in the ground to treat stormwater, but also recognizing green infrastructure as a resilient nature-based solutions, which really can be applicable within highway right-of-way within the correct situations and environments. And then also we talk about non-structural BMPs, which are often used in conjunction with structural BMPs to improve water quality. And this is storm drain cleaning, sweeping, elimination of groundwater inflows, channel stabilization. And there's many resources out there for urban drainage design. So as I mentioned, HEC-22 coming out soonish. If you heard my presentation yesterday, HDS2 is also being updated. And one of the things we did with the update to HEC-22 is we tried to make sure that both publications were really on the same page, and any discrepancies in recommendations or guidance were taken care of at that time. So, regarding detention basin design or any hydrology. So with both publications coming out on a similar timeline, they should mesh together really well. Of course, HDS4. I have to plug NHI courses while I'm up here. So the urban drainage design, there's a virtual option. They're both really good courses. We're in the process of updating them right now, but the content's all still right there. So it's still encourage everyone, if there's an interest, attend in person if you want to request it, can host it, but the virtual is a great option otherwise. And then Hydraulic Toolbox does most of the calculations that are presented in HEC-22, minus the energy grade line, hydraulic grade line calculations. There is a free WBT that NHI offers that walks you through the various calculators on the Hydraulic Toolbox, so definitely check that out. And then, of course, the tech note. So FHWA developed new curb opening equations after some research indicated that the existing equations may not be conservative enough under some conditions. So I think with that, if you guys are all still awake, James will actually present some equations.
Sure, thanks, Ryan. All right, so I do have to say, I don't have a lot of experience presenting equations. There's been some professors who have made it fun and exciting at this past week. I don't know if I'll do that, but at least I'll make it quick. But anyway, yeah, so as Ryan mentioned, back in June, FHWA released our new tech note, curb opening, inlet, interception on grade. And I was not around for this. This is before my time, but apparently back in the 2018 NHEC, Texas DOT had done some research. They had experience with this equation, equation 422 and HEC-22, and they found that it was not, it was under-predicting the amount of flow that a curb inlet could capture. And apparently they ambushed Joe and then say, what's up with this equation in the HEC-22? And then Joe called up Cornell, we're in trouble here, let's research this. And then Cornell put together his little army of CFD researchers and studied this issue. But we came up with some good results, which I will present here, that were published in this paper. So as you can see here, one of the issues, so the big issue is that the equation 422 is originally derived by Izzard in 1950, and it assumes a linear head between the up gradient end and the down gradient end, and that's not the case. Oh my gosh. Well, we got a practical joker over here with Ryan. I made the joke that we can make the presentation more exciting by putting Pennywise in the curb in the inlet, and apparently he did it. So anyway, that's a surprise. This behind Pennywise here, you can see we have some definitions, and you're familiar with the cross-sectional slope and the longitudinal slope and flow. The L sub T, that is 100% capture. So that you may not be as familiar with, but that'll come into effect later. So the researchers, they conducted modeling. The research that Texas DOT conducted, that was with Shala, and then there was another research with Mohammed. They did physical experimentation that showed that it was not being captured and it was not exhibiting that linear slope across. And so our researchers, they took that research, they tried to mimic it in CFD. They succeeded. They found out that there's a parabolic curve here, and it's based on a K ratio. And the K is a ratio of the initial water depth at the up gradient end, and E, the specific energy right before the curb inlet. And so this ratio basically so the equation, the height here of the water is based this Y. It's if you take the non-dimensional version of this, that's based on K times the 100% minus X, so that value squared. So that's the parabolic equation. But you can tell, so then at the end, when X is very big, that 1 minus X is very small, squared, it's almost 0, so that changes that profile. So that's sort of what we found. So once we found out that relationship, we tested for 3 lengths, 3 curb inlet lengths, 5 feet, 10 feet, and 15 feet. And we did 7 longitudinal slopes from 0.001 feet per feet to 0.05 feet per feet. And then we did 3 cross slopes, and that was from 0.02, 0.04, and 0.06 feet per feet. But what we ended up finding out, the CFD researchers found out that that slope, the cross slope had very little influence. So that actually did not come into effect at the end there. So there it is, the big equation. And I already mentioned the curb opening inlet is for 100% capture, that's LT. You have Q is the flow captured by the inlet. E is the specific energy I mentioned before, and then you have this M value, which is based on K, and then we have these 2 adjustment factors, which I'll discuss later. In addition to this equation, we found out a way, based on the modified Manning's N equation in HEC-22, that you could substitute the specific energy E with these gutter parameters, the slopes. So you can do it either way. So we had 2 different ways of doing this calculation. And so how do we evaluate this equation? So we went ahead and we took, so equation 8 is, equation 8 is the recommended equation that you just saw. Equation 12 is the version that has the cross slope or the slopes plugged in. And then the X here, that is the original equation in HEC-22. And so we did a 1-to-1 match line, and what we did is a simulated discharge is the CFD modeling. So they put in the slopes, they put in what they wanted the 3 inlet sizes, 5, 10, 15 feet, and then they just increased the Q until it was 100% capture. And you can see that these two, equation 8 and equation 12, closely follow this line here. And then you can also see, then the computed discharge is the equation. So we also did the same thing. We plugged in those, we took the slopes, we took those 5, 10, 15 foot inlets, and then we adjusted the Q using the equation. And you can see here that the HEC-22 greatly overestimates that amount of flow. And it's about, while these are about in a range of 0.98, 0.99, when we took the mean values, HEC-22 averaged 1.33. So it was much greater than we were seeing in the simulated discharge with using CFD. And then one other thing, quick thing, if you saw, remember at the beginning there was the risk modification factor. If you zoom in to this line here, you can see that the equation 8, equation 12, the recommended equation, is very close to that line. we can put a little risk modification factor, like it's 0.88, and that'll push these values beneath the line, makes the equation a little bit more conservative for design. So the application. So unfortunately, unlike the HEC-22 equation, it's a little trickier. You have to assume a curb inlet size to get that K value, and then you have to do sort of an iterative approach to get the final result. And so that's documented in the tech note, that methodology. You can pull up the tech note. There's two examples. It uses both equation 8, and that's the recommended equation, and then the alternate equations in there, and then we also compare it to HEC-22. So you could go through those examples and sort of see how they compare. And additionally, so there's an appendix in the tech note where we take this equation and we apply it to these other problems in HEC-22, 100% capture, composite depressed gutters, locally depressed gutters, and combination inlets. You can sub this equation in, but we haven't done any CFD research on it. It's not, that's sort of the next step. So, but there are examples if you want to do that. Limitations, there are some limitations. It's based on basically what we modeled in CFD. So we have obviously the longitudinal slopes between 0.1 and 5%. I mentioned before that we did the cross slopes up to 6%, so even though that had no effect, we still recommend that you stay in that range. The curb opening lengths, we only tested up to 15 feet, but 10 feet and 15 feet were pretty similar. You'll see that they use the same K equation, and we're sort of confident that that can be used up to 30 feet in length. I would like to add, the equation in HEC-22 is not going anywhere yet. You can still use it. This is an alternate, it's an extra tool that might produce more accurate results. So that's sort of how that stands. You can find the tech note. You can, by Googling, you can either Google FHWA, curb opening inlet tech note, or you can go to Google TFHRC, hydraulics lab. It's on our publications page for download. And I think that's it. So, any questions for me or Ryan?
Questions?
Yes.
Are you going to go for higher longitudinal slopes?
Is that the plan, Cornell?
Well, we initially had just to 4%, and we had bumped it up to 5. If that's really, if that's needed, I think that's too high. So,
Yeah. We had many back and forth with Resource Center and with Roger Kilgore wrote the tech note. So we tried to factor in what designers would need, but there's only so many simulations we could run.
Yeah, it's not the highway longitudinal slopes, it's the side streets that we need to collect water on. They can come down pretty steep.
Okay. All right. That's good to know.
Other questions? We've got about 3 minutes.
Yes.
So how did so you did 4, 6, or 4, 8?
For
The curb length openings.
the curb length openings were 5 feet, 10 feet, and 15 feet.
5, 10.
Those were the default ones that we modeled. So, and I think that was sort of based on what Texas was looking at. So.
James, quick
Yep.
question for you. Did you have transitions coming into the inlet opening in the curb as part of what they did for the research? Meaning, so it's just before you get to that opening of the curb inlet, there's a transition in the gutter to kind of bring the water into it in more of a flume type scenario.
I don't think that was the case. I think we just set it up far enough back that it could establish uniform flow, and then it's just sort of hit that up gradient end and went in. So, yeah. Up in the back.
well, all these updates spill over to HEC-21 as well.
It'll take a while. I think he asked if they're spilling over into HEC-22. I'm not sure how long that will take. Or 21.
One concern we have is that the equation 422 will be also used for sloped drains, and that's something we discussed with him. So make sure that this equation is universally applicable.
One more question. All right, give a round of applause.